Whenever you see a tube, you want to apply Bernoulli's equation. Well, the first question is, which Bernoulli? Is it Jacob? Is it Johann? Or maybe the other Johann? Or possibly Daniel? In fact, it is Daniel. Daniel gave us the Bernoulli equation. The Bernoulli equation considers a tiny volume element. Mathematically, you would say an infinitesimally small volume element as it proceeds through a tube, or more technically speaking, through a laminar flow. So at the end it'll be over here. And it says that something stays constant, namely the sum of pressure, 1/2 fluid density, maybe water, this might be water flowing through here, which is a very common case. So we have the density of water, 1000 kilograms per cubic meter, times the speed of the volume element at this time, or at this point in the fluid. So we've got a V at this point, and we've got a V at that point. So this might be V1 and this might be V2, and we could call this point 1 and this point 2. And finally, adding to this sum is a potential energy term, rho times gravitational acceleration times height. So this is a flow in the horizontal direction, so our height scale is up the paper. And you can see that this looks very similar to an equation about energy. And in fact, this term is related to the kinetic energy. In fact, it is the kinetic energy of this tiny volume element. This is the potential energy. And the pressure, if you multiply that with the volume of that element, can be interpreted as the work that is applied to the volume element. And Daniel Bernoulli says that the sum of these three contributions to energy are always constant, independent if you look at the volume element at position 1 or at position 2. Now, does that apply to all fluids? No, it doesn't. One has to be a bit careful. It certainly doesn't apply to this fluid. Well, you might say, this isn't even a fluid, it's a solid, just like the yellow bar next to it, the yellow ball next to it. Well, this funny fluid sometimes behaves like a solid, and sometimes it behaves like a fluid. And we call this a non-Newtonian fluid. That's what we don't want. We don't want non-Newtonian. We need Newtonian flow. We want things like water, ethanol, or even honey. That's one of the four N's. There are four N's to consider. The next N to consider is viscosity. We want non-viscous flow of our fluid. That means the little molecules which make up the fluid that streams along, these little molecules should not interact with each other, at least not much. We don't want interaction between those molecules. Honey is an example where they do. Honey is very viscous. We don't want honey. Honey is not a good case. Another N to consider is non-turbulent. We want non-turbulent flow. We want laminar flow. We want this type of flow where the streamlines are parallel. We don't want a flow which is turbulent like this. In this case, the particle path, these little molecules, the path of these little molecules cross each other. That's what we don't want. That's also a very interesting phenomenon, and in fact it's quite important in many aspects of our life and in technology, like in flight, for example. But in order to apply Bernoulli's equation, we want laminar flow, not turbulent flow. So there must be one n left. We've got 2 in here, the formal number 2 there, the formal number 3 there. We need one more n. What is the last one? We want non-sticky, or no surface tension. We don't want the fluid to stick to the walls. This is our tube. We don't want interaction, or at least not much interaction, between those molecules and the walls. We don't want that. That's referred to as surface tension. Now, this is an idealization. However, in some cases, in many cases, oil might be another one. Most oils would fulfill these 4 approximations in very good manner. That they are Newtonian, that they are non-viscous or almost non-viscous, almost non-turbulent, and almost non-sticky. And then, if you have got that situation, you can apply Bernoulli's equation. How do you do this?